Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Advanced ODE theory proves that paths exist. Matrix flow calculates volume expansion. Green's functions invert operators. And
Hey everyone, I am absolutely thrilled to guide you through today's explainer. We are going to be looking at something truly profound. We're taking a journey from just plotting your basic mathematical trajectories all the way up to understanding the complex, beautiful systems that actually govern the reality we live in. We are literally looking under the hood of the universe itself by exploring the advanced theory of ordinary differential equations. Okay, let's just dive right into this.
I want to kick things off by posing what might just be the ultimate physical question. How do we mathematically guarantee the future? Like, does a single, unique future state actually exist for a physical system based on exactly where it is right now? Or are there just infinite possibilities branching out infinitely in front of us? Well, it turns out differential equations hold the absolute key to answering this.
Here's our roadmap for the explainer today. We're going to start with the quest for unique solutions, then we'll scale up to second-order analytical solutions and tackle linear systems instability. After that, we dive into boundaries and Green's functions, explore Sturm-Liouville and Hilbert spaces, and finally, bring it all together by going from local to global.
All right, our first stop is Section 1, the quest for unique solutions.
So our very first conceptual hurdle is establishing if an initial value problem actually has a reliable single solution. There's a fascinating contrast between two foundational theorems here. Peano's existence theorem gives us some hope. It proves that if a system is merely continuous, well, at least one future trajectory exists. But here's the catch. Mere continuity can lead to infinite branching paths, and we don't want that. That's where the Picard-Lindelof theorem steps in as our mathematical anchor. By using contraction mappings on complete metric spaces, it guarantees that our physical system has only one true, unique future. The secret sauce to how Picard-Lindelof pulls this off is something called the Lipschitz condition. Basically, this is a strict constraint that restricts how rapidly vector field orientations can shift as you move through space. Without it, you get what mathematicians call non-uniqueness. I actually like to think of this brilliant little condition as the literal mathematical wall standing between a predictable deterministic universe and just pure, unadulterated chaos. But wait, once we know our future is unique, how do we know it's not just going to violently collapse or spiral out of control? Enter Gromwall's inequality. This acts like a leash, bounding the growth of a function. It provides continuous physical stability, proving that our systems won't just spontaneously blow up to infinity. In the math world, they talk about solutions escaping from compact sets, which honestly sounds like an elaborate magic trick, doesn't it? But really, Gromwall's just the rule, ensuring our trajectories behave smoothly as time ticks on. Moving right along to Section 2, second-order analytical solutions. Now, as we scale up to second-order equations, things get significantly trickier. We have to start mapping out the system using infinite series. We categorize the system's behavior based on its singularities. Think of these like different types of terrain. First, you have ordinary points. These are your smooth-sailing, well-behaved zones. On the extreme end, you have irregular singular points, which are essentially chaotic, unmapped wilderness. But sitting right in the sweet spot are regular singular points. They're manageable hurdles, and mathematicians systematically attack them using a totally brilliant technique called the method of Frobenius.
To actually use the method of Frobenius, you absolutely need the indicial equation, f of r equals 0. Why is this so crucial? Because the roots of this specific algebraic equation are like a DNA test for the system. They tell us exactly how our physical solution is going to behave. Depending on what those roots are, our solution might play nice, or we might literally be forced to introduce complex logarithmic terms just to keep mapping the system accurately. Let's keep zooming out. Section 3, linear systems and stability. So we're moving away from single equations now, stepping into multidimensional linear systems that map out massive, dynamic networks. To navigate these massive networks, we rely heavily on the fundamental matrix. You can think of this matrix as the ultimate tracking device. Its columns capture the entire dynamic behavior of a complex, multivariable system. And this perfectly sets up how mathematicians use the Abel-Liouville formula. By taking the determinant of this fundamental matrix, we can track exactly how a complex system's entire volume evolves, shifts, and flows over time. Of course, knowing where it flows is one thing, but we also need to know if our system is safe. We can look at two types of stability here, which are determined by the eigenvalues of the system matrix. Lyanov's stable means the system might oscillate, but it does so safely within set bounds. Asymptotically stable, on the other hand, means the system eventually calms down completely to zero. To put that into real-world terms, imagine a huge suspension bridge swaying in a heavy wind. As long as it sways safely without snapping, that's Lyanov's stability. But when that wind dies down and the bridge perfectly settles back into absolute stillness, that is asymptotic stability.
All right, on to Section 4, boundaries and Green's functions.
We are officially leaving the realm of open-ended initial value problems and stepping into strictly constrained spaces. There is a direct quote from the source material that really hits the nail on the head here. Unlike initial value problems, boundary value problems may possess a unique solution, infinitely many solutions, or no solution. The whole rule book of the universe changes here. When you slap boundaries on both sides of a timeline or a physical space, predicting the outcome becomes a completely different game.
So, how in the world do we solve these highly constrained systems? We use Green's function. What it does is elegantly convert clunky linear differential operators into neat, compact integral operators. If you think about it, Green's function is basically a mathematical skeleton key. It unlocks our ability to solve these stubbornly constrained, non-homogeneous systems by letting us integrate over the entire domain.
Check out the properties of Green's function here. I want to highlight that third point, the calculated derivative jump discontinuity. This is just fascinating. The function itself stays continuous, right? But its derivative has this sudden, sharp jump exactly at the source point. In physics, that jump discontinuity beautifully represents a local physical impulse. You know when you pluck a guitar string, that initial sharp snap? That's what this represents mathematically, a sudden burst of energy rippling outward across the boundaries.
Let's take it up another notch. Section 5, Sturm-Liouville and Hilbert spaces.
Okay, get ready for the ultimate conceptual crescendo. We are stepping deep into the realm of self-adjoint operators. The spectral analysis of Sturm-Liouville operators hits 3 massive milestones. Number 1, it guarantees all eigenvalues are real numbers, which, by the way, is absolutely essential if we want observable physics. Number 2, it establishes that the eigenfunctions are completely orthogonal. And number 3, it proves spectral completeness in an infinite dimensional Hilbert space. This is huge. It shows exactly how simple bounded waves can build into infinite generalized Fourier series capable of describing virtually any state imaginable. Now, how do we find the absolute baseline of a system like this? We use the Rayleigh quotient. This neat formula calculates the smallest eigenvalue by finding the minimum possible energy of the system across all admissible functions. And why does this matter so much? Because nature, as it turns out, is notoriously lazy. Nature will always seek the lowest possible energy state. The Rayleigh quotient is exactly how we calculate that foundational bottom floor state mathematically.
And finally, Section 6, from local to global.
Let's bring this whole journey together. This breakdown beautifully illustrates the bridge of logic we've walked today. We started out tracking tiny local points using Picard operators. Then we ensured global dynamic stability with fundamental matrices, moving on to representing bounded systems with Green's functions, all the way up to mapping absolute Hilbert space completeness with self-adjoint operators. If there is one crucial takeaway from this explainer, it's that mathematics scales. Figuring out how to solve a seemingly simple trajectory equation laid the absolute bedrock for humanity to understand the incredibly complex physics of the wider universe.
It's this seamless, breathtaking transition from analyzing a single local point to unlocking global operator theory. I want to leave you with one final, totally provocative thought. When we look at Sturm-Liouville theory and Hilbert spaces, we aren't just doing abstract math. We are looking at the foundational language of quantum mechanics. So, you have to ask yourself, are these exact infinite-dimensional equations actively calculating the quantum states of the universe right now, every single second, just quietly running under the hood of reality? Man, I hope this explainer leaves you in as much awe of the mathematical universe as I am. Thanks for joining me, keep learning, and as always, keep looking under the hood.
Like what you share.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious mind.